So today let us see regarding the algorithm of data encryption standard, the DES algorithm. So this is assumed to be one of the modern cryptography technique that is still used today for encryption and decryptions in order to make our data secure by providing those CIA threads here. So how actually we do this one? I told you that this DES algorithm is also a block cipher technique, and is one of the technique that follows the fiscal structure that we have done earlier. So if you look at this overview diagram of this DES algorithm, so if this is round 1, round 2, and we have up to round 16 here, and round 16 here, by default the DES algorithm, in a DES algorithm, the plain text bit, the size of the plain text is of that particular block is of 64 bits here. So we are now doing the DES algorithm. So here we are now not assuming the number of bits as we have to do earlier, but here we have this 64 bits in a single block of the plain text here. So we will be doing block by block the encryption and a decryption technique block by block here. So in a particular block, that particular block consists of 64 bits here. So I have written as 64-bit plain text. Okay. So what actually is, so I told you this one, we will be considering all the rounds up to the 16 rounds here. Up to the 16 rounds, why we are adding the increasing the number of rounds is that we are adding the complexity to the we are just adding the problem of diffusion and confusion in encryptions here. Okay, so we are just adding the complexity again and again. So even in round 1 also we could get a ciphertext, even in round 2 also we could get a ciphertext, but we are still continuing up to round 16 by default in order to have a maximum complexity so that it is very impossible to cryptanalysis or break the encryptions here. Okay, so like what we have studied in the fiscal structure, we have this particular round for encryptions, and also we have the 16 same round for the decryptions here. And also here one more is that we have the, I told you this one, that in the fiscal cipher structure there will be a key generator. So this is the key generator step here. Okay, so this particular step is the key generator step. So this will generate the key and it will provide the sub keys. Suppose this is the parent key. From the parent key, by using this particular procedure, we will generate the sub keys for all the 16 rounds. So all the 16 rounds will have different sub keys, and that particular sub keys will be generated by this particular module here. Okay, so even the size of the key previously it was taken to be 64 bits here. Okay, the size of the original key is of 64 bits here. The size of the plain text is of 64 bits, and the size of the key is of the 64 bits here. From that particular 64 bits, we remove the parity bits here. Okay, so if you know what is a parity bit, the 8th bit, every 8th bit is removed here. So there are 8 bits here. So 8 minus 2, it becomes 56 here. Okay, so we have, if we remove every 8th bit, then that is 64 minus 8, then we have this 56 bits here. So that 56 bits we are using for the early key generation steps here. Okay, it is not the case that we are using this 56 as a key here. From this 56 key again, I have to generate the sub keys here. Okay, so you must remember that from the 64 key, from 64 given original key, I reduced to 56-bit keys here. How? By subtracting the 8th bit, every 8th bit. Okay, every 8th bit means the first 8, then 16, and so on. They are removed, and then we have got only 56 bits here. Okay, so if you look at this particular modules here, in this particular module, that particular 64 bits, in order to make it more complex, you can add so many other procedures here. Okay, So by default in a DS algorithm, what actually it do, it goes for an initial permutations here. Okay, out of the number arrangement, for example, you will be having the first bit, second bit, third bit, fourth bit, and so on. So the first bit can be 0, the second bit can be 1, the third bit can be 0, and so on. So here the permutation means this arrangement are changed here. Okay, we are not adding any extra bits here, but within that particular 64 bits we are just changing the positions here. Okay, for example, 1 2 3 4 5 6 7 8, then 9 10, and so on. So this again, if we change the position, means 9 bit comes here, 10 bit comes here. Okay, or second bits can be coming at any other positions here. So like this one, we perform the initial permutations here. The IP stands for initial permutation. Okay, the initial permutations here. So in that we are not adding or we are not removing any bits here. So after the permutations we also get this 64 bits here. Okay, since I cannot draw each and every bit, so I put an arrow mark and then put this one here to represent the number of bits here as an approximate bits here as 64 bits. Okay, then they will follow round 1. Inside that round 1 it will go through certain procedures here. Okay, so there we also have the round functions. If you remember the official structure, we have the round functions. Inside the round functions, what are the changes to be done? We have the swapping operations, we have the XOR operations, we have the round functions and all. So those everything should be done in round 1. After that we have round 2 and so on up to round 16. At last those 32 bits at the left hand side and we have 32 bits at the right hand side here, that we know that we interchange it. Okay, we swap it and then we got this 64 bits patterns here. Okay, that pattern, since we have done the IP initial permutations at the first, we have to perform the inverse of that initial permutations, and that particular result will be the 64-bit ciphertext here. That particular result will be the 64-bit ciphertext here. Okay, since we perform the initial permutation, at last you must keep the inverse of that initial permutations here, and then we will generate a certain pattern of 64 bits. That 64 bit is nothing but your final ciphertext here. Okay, final ciphertext here. But the case is there how actually we supply the keys here. Okay, so if you look at this particular diagram, so from that 56-bit key we have a permuted choice 1. There is a default table of permutation. Okay, there is a default table of permutation for use for DS algorithm. So that particular table we term it as permuted choice 1 and permuted choice 2. So that using the permuted choice 1 table, we interchange or we shift or change the positions of the bits here. Okay, change the position of all these 56 bits here. Okay, 56 bits. Then again we are not removing or we are not adding any other bits, so this 56 remain as it is. Okay, so then the case is how actually the K1, the first key, is generated. So according to the round we have used here, according to the different round we have different shifting operations here. Okay, we have different shifting operations. So if you look at this particular diagram, this is the round number and this is the number of bits rotated here. For round 1 we must circularly shift to the left side by 1. Those patterns of bits here we must shift it. Okay, we must shift, circular shift by 1 bit, then the pattern changes here. Okay, pattern changes here. And if it is a second round, then we shift by 1. If it is third round, we shift by 2, and so on. Okay, up to this 16th round here. So for every round the shifting are different. For first round it is 1, second round it is 1, again the third round is 2. So that since we are continuously shifting the 56 bits here, then we will get the different keys here. This K1 up to K16 will be different. So up to the round 16 we are continuously shifting either by 1 or either by 2 bits here. Okay, this is the default number of rounds and the number of bits rotated in each and every round here. Okay, so if you look at this particular diagram here, so this is nothing but a permuted choice. Okay, here is the permuted choice 2. So like this one, we also have the permuted choice 1. So they will arrange the 56 bits here, and then the 14 bit will come first, the 17 bit will come second, and so on. So according to this, we have to fill the number of bits here. So this kind of tables are predefined. This kind of table are predefined. So since we cannot remember all its name here, so we go by its nomenclature as the PC1 and the PC2 here, the permuted choice 1 and the permuted choice 2. So let us see, if you look at this one, see here, for each and every one we have to circular shift to the left side. Circular shift to the left side, by how much it depends upon the number of round used here. So this is the structure or an overview structure of your DES algorithm. So we will be seeing inside what is done inside is round 1. Okay, what is done inside is round 1 and how actually we perform the operations inside is round 1 here. Okay.